Um, we have this model on the screen right now, and what we want to do is to be able to generate the model of this system. It's a mechanical system, and we would like to see how the bone graft model is generated, uh, how this model, once we generate, we enter into CAMG to do a computer simulation. So let's concentrate for now on how do we go actually about generating the model. Let's go see here the kind of components that we have. That is going to be the first step that we have. In fact, I'm going to write it down in here, step number 1. I'm going to say what you need to do is to recognize the elements present in the system. Okay, very good. And so why don't we do that in here? You're gonna see that on this crash test model, we have this car, which is basically an I element in here, and that we could say this is an I element over there. We have this seat belt in here, which has a damping, and it has a, a spring, so because it's compliant, so you could say, okay, those are C elements. Why don't we just maybe change the color here so that we can, so this is a C element over here, and this over here is going to be the the damping here. This would be a resistive element, obviously. You have an I element, you have also the person here. So the mass would also be an I element in here. And this would be a C element in here for this spring. And this would be also an R element over here. See? We are going to do the simulation when the car hits the wall. So not when it's separated, because then it would be a nonlinear system. So why don't we just bring the wall to it just so that we know where we're going to start, like this, yeah? Okay. Having done this and recognition of the different elements that we have on the system, the next step that we do is to so let's go number 2. Step number 2, we're gonna say use a one junction to represent the distinct velocities. All right, so let's do that. Let me move down here, and I would say the velocity of this mass over here, I'm going to represent it with a one junction, and I will call this would be the velocity of the car. So why don't we put B of the car? That's one. This, of course, is the car is going this way, like this. I'll say, so it's B of the car. The person is also going in that same direction. So this one here is going to be the velocity of the person. And so for that velocity, I also going to use a one junction here. I'm just going to put it here like the one velocity of the person. So those are the two independent bodies that have velocities. But also here, keep in mind that we need a reference point. I would think that it's constructive to write that we have a velocity of the wall equals to 0 as another one. So those are the velocities of the system, including a reference point, so that we can have a systematic procedure and also represent that so that the model would have a reference point for the other velocities. So that's what we have. So we are done with step number 2. If you go to step number 3, step number 3 would be, I would say, attach to the one junctions the elements that experience those velocities. Very good. So what I'm going to do in here, let's just change our pen color, and we say, okay, here's the velocity of the car, so I'm going to attach the car. Right there, this is an I element which has value big M, yeah? And then over here, I have the other one. This is also an I element whose value is little m, lowercase m. That's the person. Here we have is a source of flow, yeah, with velocity of the wall equals to 0 as a value of this. That's what that is. Now in here you have that those are all the elements that move at the velocities that we have in here. Yeah. Step number 4, we are going to say, step number 4, I'm going to say use a zero junction to represent the velocity differences. Velocity differences. Or you could say safely use relative velocities. You see between the elements. And I'm going to say let's see, what is the word elements? Good. And represent those with one junctions. What does it mean? Let's just do a translation, basically, or execution of instruction number 4. Right? It says between the car and the person. So if we assume that the car is moving and whatever the car does, the person will follow later, then we need to establish the velocity difference between the velocity of the car and velocity of the person. So it says use a zero junction to do that. So I'm going to put the 0 here and use the arrows this way, and this difference, like this, represent with a 1, which is velocity of the car minus velocity of the person. That's what this is saying. We use a zero junction to represent the difference, And of course, that difference is also represented by a one junction. In between the car and the wall, there is also another situation here. So I'm going to put a zero junction over here, and then we're going to go here like this, and then this, of course, velocity is zero. Here, we're consistent with the direction. The car is higher than the velocity here, so this is going to be the velocity of the wall. This is the velocity of the car. So the difference with the 1 is going to be v of the car minus v of the wall. Yeah, that is what the step number 4 is saying. Okay, so with step number 4, we have used zero junctions to do the velocity differences, and of course that difference also with one junctions. Okay, it's taking shape already, and we only need just a few more steps. Let me just clean up this little thing here, and then we'll go and we need to attach the elements that represent that see those velocities. So that's going to be step number 5 in here. Um, Hold on for a second. I think we need to get back to the to writing. So step number 5, I'm going to say attach the elements that experience those relative velocities. Why don't we say those velocity differences, parentheses, we're going to call it relative velocities. When we speak about relative velocities, it means a velocity of one mass with respect to the other. So in this case, you could see that very clearly between the car and the person. So here's the person, this is the car. Between these two, we have this difference in velocities. But these elements, in fact, see that difference. Like here, this is going to be the C element in here with this value of C is 1 over K, or 1 over K sub 1. And then also we have a resistive element R with value B sub 1. Yeah. And that is on one side. But over here on the bumper, between the car and the wall, also this velocity difference is seen by this C element, which is this spring here with value 1 over K sub 2, and this other one in here, which is an R element with value B sub 2. Very interesting. We have, from all practical purposes, have actually finished the model. There are certain things that are not in here that I would say at this point they are optional. You can do them for verification purposes, or you can let ChemG do it. There is two of those actions. One of them is the numbering of the bonds to just have the computer have a reference as to what it is, and the other one is the causal marks. But what I'm trying to say is, if you have the model to this point, to this stage, ChemG will do the rest for you. but in here is the 6 numbering of bonds and causal marks. This you could say CamG can do this for you. Okay, so if you want, like I said, you can put them in here, or you can get the computer program to do it. So with that explanation in here, if we don't put any of the numbers, CamG will choose for you. But if you want to have your own numbers, then you need to put them in. So what I would do is um, we could try it in such a way that we we put in our own numbering system here, and we tailor the bond graph with the entering into CamG with that. So what yeah, let's do that. Like I said, other ways, you can let CamG do the whole thing for you. You don't have to do what I'm doing right now before you put them in. But let's say you do, and this is just the numbers, the order doesn't matter, um, in which you enter them. Of course, they would be generated in the way you enter them. But I mean, the numbering system doesn't matter. Anyone can have any number. So we are ready to go. With this in mind, we go directly to the computer program, and we're going to reduce this to a point where we can only see the bond graph model for purposes of entering it into my computer simulation scheme. We can even reduce it a little bit more so that we create some room for the software, the actual software that would do this. So I'm just going to perhaps do yeah, this is clear enough, right? See, like that. And then we have plenty of room on both sides in here. I'm gonna do it as efficiently as possible. There we go. So this is our task. Now we go over here and we say, okay, we need to go and look for the CamG software, of course, and then click in there, and then you're gonna have this, but we don't need it this big. So I am going to click on new because we need to do a new model, and then maybe we'll move the window a little bit so that we are able to leave some room for the model here. There we go. And then we have this one over here. Yeah, I think that's just, I think we can do it there. There we go. So I could start with the one junction that contains bond number 1. So to do it exactly as it is on the picture in there. So this is the I element over here, and then go click here, click there, and that's number 1. And then we go and do the 0 over here, like this, and then you do click here from here, that's number 2. And then we go number 1 over here, and do you see what I mean? It's following exactly what you have on paper. You are going to enter it now for bond number 4, which is this C element over here. You enter it in the sequence that you want, but also from 2, always from 2. So you have the R element in here, which is the number 5 over here, and 5 goes from 1 to R, and it does the 5. and then you have the 6 goes from 0 to this 1. So we write the 1 and then from this to this. And you could see one thing at this point, that the causal marks are automatically being assigned by CAMG as we go along. As the model is being completed, every time you put one element is totally recalculated. Here, if you were to stop here, this would never work because the causality does not complete. And then it's a system that you need to complete. But see here, you put the I element, this does, but this is not the whole system in here. This, we are up to number 8 over here, and number 8 is going to be this one that goes from 1 to the 0, and then you have 9. We have to do this 1 over here, and you go from here to here, and then we have gone to another 1 down here. So this is a 1 from here to here, that's number 10. And then we have the C on number 11. So then you put that C over here, then from here to here. And then you have this number 12 is this R element, which is over here. Do you see how it takes shape? And pretty soon we are almost done. And here all we need to do is to enter this SF, and consistent with this, we complete the entire thing. So one thing happened here. Something happened here. We have an element that has a red marking here. And it's interesting, it's actually good that this happened, because in here we have an error. This has a derivative form in here, that's what it means. When you see any red thing, you could say explain what's happening in here. And the computer will actually explain to you what it is. Comes with a little stethoscope, and you'll get a message as to what it is. This is derivative form. So let me show you how that message looks like. I'm gonna move it up a little bit. In here, do you see? See where's our explanation in here? I want to make sure. Yeah, if you click over here, see right there, this says derivative form. It is behind here, but that's the message here. What happens is that you see this junction here is not supposed to be a 1, it's supposed to be a 0. And we made that mistake, so we need to correct it. Delete this, we need to delete this. See, it's supposed to be a 0 instead of a 1. Inadvertently, I did that, so let's just erase this, and now you can see how you correct things. This automatically is set, and it will recover the same numbers that you had. And now this is supposed to have fixed this, and how come this is not? Anybody? Well, guess what? This whole structure, I'm going to show you. CAMG is very smart, and actually it's good that this happens, because it shows you how you can mess things up. Do you notice what I did? This is the first error really is this structure here is actually attached over here, not over here. And that's the problem. But I'm going to show you a very interesting way of fixing this thing, that you can actually use the tools of CAMG precisely to do this kind of corrections. So what I'm going to do is, the first thing I need to do is to delete this and then move this over. So I didn't have in mind to do this because I just would assume the first time, but actually this is good because helps us see the features. So in here, if you say move, you're going to move a segment, which means a set of bonds together. And this one is here, see? But there's this cannot be a 0. It is a 1. When you look at the model, it's a 1. So we better not commit the same error. But I think the fact that this happened, it actually points to the fact that, first of all, we're not perfect. Second, the program has a way to correct these mistakes. And so this was too bad. I entered in the wrong place. But now this is perfect. See, now that we have entered the model, everything is done correctly. If you look at the model on the left-hand side and you compare it with the model on the right-hand side, this whole thing is perfectly fine. So what I was trying to say is that you can have these models with the whenever you see red in there, get an explanation using explain. But also at this point, it would be very important to use some features that are really helpful to you. For example, this peak. If you pick anywhere on this model, it gives you the equations of the system, see? Equations of those elements, and the equations of the junctions. And see, anywhere you go, this I, even the derivative, which is a differential equation. And in here, the equations of the junctions, the equations of the C, which also has a derivative here, you see? In the entire, this allows you to see that this picture that we have is very different than the picture on paper. Because the picture on paper, it just indicates how the elements are connected, but the the one in ChemG actually has the equations behind it. Now we could have assigned the causality on this picture on the left and see how and verify it with this. Or we can do the reverse. We can assign it now to verify what ChemG did. So we can do both ways. But before we do that, I would say go to this part where it says block diagram. What happens is if you click on the elements, on each element, it's going to give you the equivalent bond block diagram of the junctions, the equivalent block diagram as the element would be in Simulink. So this is a way to verify that you understand the equations of the system as well. The last thing I would like to do is to go ahead and actually here assign the causal marks just so that we can see how we did that. I think this would be a SF in here. Okay, hold on for a second. I think we want to make sure that our mouse does not give us problems. So now it is. The left window is active. So I am going to use a red pen. You can start first. You assign the sources here. See, the moment I did this flowing here, this one has to be like this. And then we go to the elements in integral form. The moment that I assign this flow, the other ones have to be like this. And you propagate it as much as you can. So in this one over here flow, this has to be like this. So you see this has two flows like this. This one has to be like this. And the moment you set the flow here, these other two have to be like this. and then we go over here, see in the 0, it requires one effort input in here, and that sets the flow for this, and this has to be like that. If you compare the causal marks on the red that I just did with the ones that are over here, they're exactly, perfectly the same. So this is how we enter the model here, and in next video we'll do it how we do the simulation.